Having learned about the geometric meaning of determinants and how to compute determinants, the next thing we'd like to do is to look at the properties of determinants. What are some properties of determinants? So we are going to look at this in the line of determinants of a product and determinants and invertibility, which we've been talking about, here and there. So the determinant is a number associated with a square matrix that provides important information rather about solvability of systems of equations, invertibility of matrices, geometric transformations, area and volume scaling. So for a square matrix A, its determinant is denoted by det A or absolute A, which I like. I like the second rendering a lot. So let's go ahead and talk about determinant of a product. What happens when you multiply? When you multiply two matrices and you want to look for the determinant, what do you get? Okay, let's see. So the theorem is this: for any two square matrices A and B of the same order, determinant of A multiplied by B is equal to the determinant of A multiplied by the determinant of B. This is called the multiplicative property of determinants. Okay, so that means if you have two different matrices and you multiply them together and you find their determinant, what you get is going to be equal to the product of their individual determinants, right? The meaning of this is that determinant of a product equals the product of determinants. Okay, instead of computing AB first, we can compute the determinant separately, right? So if you are looking for the determinant of AB, because multiplying them together can waste your time, so you can just find the determinant of A, find the determinant of B, and multiply together. That's the determinant of AB easily. So we have some conditions though. A and B must be square. Of course, you can't find the determinant of anything that is not of a matrix that is not square, and they must have the same order. So of course, it has to be the determinant of a 2 by 2 two by two matrices or three by three matrices. So they have to have the same order. Otherwise, AB may not exist if they are not square and they don't have the same order. And the geometric interpretation is that if matrix A scales space by determinant A and matrix B scales space by determinant B, then A and B together scales space by determinant A and determinant B, because we already saw the geometric meaning that determinant is all about scaling spaces, either compressing or expanding space. Example one, right? So look at this. A is 2103. Of course, clearly the determinant of this A is 2 times 3, 6 minus 0. That's 6. And for this one, it's 1 minus 6. So this is 6 and this is minus 5. So the determinant together is going to be minus 30 if we multiply the two together. So, oh, okay, I think I was ahead of myself. The determinant of A, of course, is 2 times 3 minus 0, 1 times 0. That's 6. For B, it's 1 times 1 minus 4 times 2. 1 times 1 minus 4 times 2. That's 1 minus 8. Or did I say 6 the other time? So that'll be minus 7, not 6, sorry. Then if you multiply, the determinant of AB is going to be determinant of A times determinant of B. That's 6 minus 7, which is minus 42, easily. But of course, if you compute AB now, like 2103, 1421, so you get 4963 if you multiply the two together. So to find the determinant of AB, that will be 4 times 3, 12 minus 9 times 6, 20, which is minus 42. So, and the result is actually true that the determinant of AB is equal to the determinant of A times the determinant of B. Okay. So, okay, maybe let me go to the worksheet and form my own matrices to explain that reality. But of course, we've seen that there already, that it's actually true. So I'll use the 2 by 2 matrix to make things easier. So imagine A is 2, 3, 2, 1, 7, and B is minus 1, 4, minus 2, say 5, right? So we know the determinant of A is simply 3 times 7 minus 2 times 1. So that will be 21 minus 2, and that is simply 19, I think. Yeah, 19. Then the determinant of B is minus 1 times 5 minus 4 times minus 2. Okay, so determinant of B is simply minus 5 plus 8. So the determinant of B is equal to 3. So that's determinant of A, determinant of A. So that goes. So of course, we are saying that the determinant of AB now, the determinant of AB. Okay, let me use my own style, what I like to use. So what we are saying that the determinant of AB now is equal to the determinant of A times the determinant of B, which is 19 times 3, which is 57. So this is what the theorem has told us. But can we verify that? Because now we have AB, which will now have to be 3217, right? 3217, 3217 multiplied by 1 minus 1 4 minus 2 5 minus 1 4 minus 2 5. So we then have AB to be equal to, of course, because we have two rows here, you have to write these columns twice each. So minus 1 minus 2 minus 1 minus 2. Then this is 4 5. This is 4 5. Okay, then you now put 3 2 over the top, 3 2 3 2. Down here you have 1 7 1 7. That's fast way to multiply matrices. So AB now is just going to be equal to minus 3 minus 4. Okay, this is 12 plus 10. This is minus 1 minus 14. Then this is 4 plus 35, like that. So you need just multiply and add. This minus 3 plus minus 4, that's minus 3 minus 4. So that's just that. So AB now is equal to minus 7 here, 22 here, minus 15 here, and 39 here. Okay, 39 right here. So the determinant of AB now will just be minus 7 times 39, okay, minus 22 times 15, minus 22 times minus 15. So that's AB equals 7 times 9 is 63. That's whole 6. 7 times 3 is 21. That's minus 273, I believe. Then plus 22 times 5. That's like 11 times 30. 11 times 30. Yeah, 11 times 30. Yeah, that's 11 times 30, right? That's 330. What did we get there? 50, this is 57 right here. So 11 times 30. Yeah, so that's 330. 11 times 3 is 33. So that's 330 minus 273. So this is 7 here. Yeah, that's 7. Okay. This is 2. So that's 12 minus 7 minus. So that's 57. And that, I think that's correct. So here we got 57. Yeah. So the answer is 57. So the determinant of AB is simply 57, like that. So we can conclude, maybe I should change. So we can conclude that the determinant of AB is equal to the determinant of A times the determinant of B. That's what we have seen from all of this. So that now, if you have example 2, if the determinant of A is 0 and the determinant of B is 5, then the determinant of AB is 0 times 5, which is 0. So AB is singular. So if one matrix is singular, the product of that matrix and another matrix, no matter what that matrix is going to be singular too. So determinant and invertibility. So theorem, a square matrix A is invertible if and only if the determinant of A is 0. That means that a matrix has an inverse if and only if the determinant is 0. It also means that if the determinant is not, a matrix A is invertible if and only if the determinant of A is not equal to 0. That also means that if the determinant of A is not equal to 0, then the matrix is invertible. That is, it has an inverse. But on the other hand, if the determinant of A is 0, then A is not invertible. So the meaning is here that the determinant not equal to 0, the matrix type is non-singular. Inverse exists, yes. If the determinant is 0, the matrix type is singular. Inverse exists, no. All right. So in short, if the determinant is equal to 0, rows or columns are dependent. That is, one row is a multiple of the other or something like that. Then there'll be information lost because of redundancy. Space is flattened, and no inverse will exist in that case. So on the other hand, I will talk about the determinant of the inverse. If A is invertible, then the determinant of A inverse is 1 over the determinant of A. So if A has an inverse, right, the determinant of that inverse is going to be the reciprocal of the determinant of A. So example here, imagine that you have A to be 3 to 1, 1. So find the determinant. Determinant of A is 3 times 1 minus 2 times 1. That's 1. since the determinant of A is not equal to 0, then it means that this one has an inverse. It is invertible. So the question is now, let's find the inverse. For 2 by 2 matrix, inverse is easy to find. So all you just need to do is, for a 2 by 2 matrix, A inverse is 1 over the determinant of A. And that is, so you don't normally have A, B, C, D, right? If this is A, B, C, D, so you switch over D and A and change the signs of B and C. So this is what I mean now. Talking about a 2 by 2 matrix. So we're saying that for a 2 by 2 matrix, A, which is equal to A, B, C, D, all right, the inverse, A inverse, right, is equal to switch up A and D. So D comes here, A comes here. So it's like we are switching, we are interchanging these two. Okay. Then apart from that, you now change the signs. B remains where it is, but the sign now is negative. And then you have 1 over the determinant of A. Okay. So A inverse is equal to 1 over the determinant of A multiplied by switch up A and D, right? And then change the signs of B and C. And that's it. So that's how the determinant goes for 2 by 2. So if that is the case, then so A inverse now for the original 3 2 1 1. So 3 1 will switch 1 3, and then for 2 and 2 and 1 we have minus minus, and the determinant of this is already 1. So we have so 3 2 1 1. Let me work that out so that you can understand. 3 2 1 1, right? 3 2 1 1. So let's say we have B is 3 2 1 1. Okay, so the determinant of B, like I said, is going to be 1 over determinant of B, the inverse rather. The inverse, B inverse is going to be, what did I do the other time? Yeah, it's inverse. So B inverse is 1 over determinant of B into, right, into 3 and 1 now. So 1 comes here, 3 comes here. For 2, you have minus 2, you have minus 1, and that's it. So B inverse now is simply 1 over the determinant of B, that's 3 times 1 minus 2 times 1 minus 1 times 2, if you like, into 1 minus 2 minus 1, 3. So again, this is B inverse, which is 1 over 3 times 1, 3 minus 1, 1 times 2 is 2 into 1 minus 2 minus 1, 3. So that B inverse now is equal to 1 over 1. It is 1 over 1 into 1 minus 2 minus 1, 3. So finally, B inverse, because this determinant is 1, so we just have 1 minus 2 minus 1, 3, like that. So that's what that tells us. So that's why we have 1 minus 2 minus 1, 3. So for example, 4 now, we have a unique situation. You can see 2, 4 is a multiple of 1, 2. So first of all, find the determinant. That's 2 times 2 minus 4 times 1, 0. So that matrix has no inverse automatically. The conclusion is that since the determinant of B is 0, B is not invertible. And of course, we can see that from the matrix already that row 2 is half of row 1. So rows are dependent. So that's why the matrix is singular. Then we have productivity and invertibility. What do we say about productivity? Product and invertibility. Theorem, if A and B are invertible, that is if they both have inverses, then AB is invertible. So if A is invertible and B is invertible, then their product will also be invertible. So proof, determinant of AB is equal to determinant of A times determinant of B, not 0. That's what that means, right? So the converse is that if AB is invertible, then both A and B are also invertible because the determinant of AB is not 0, which implies that determinant of A is not 0. Determinant of B is also not 0, right? So they all have inverses in that case. I think that's a very easy thing to prove. So example 5 now, because to show that something has an inverse, just show that the determinant is not 0. That's all. So example 5, suppose determinant of A is 3, determinant of B is 5. Find the determinant of AB. That will simply be 3 times 5, 15. Then is AB invertible? Of course, because AB is a product of two invertible matrices. So AB itself will have an inverse because it has an inverse of 15. Okay? So the solution, okay, we have the determinant of AB is 3 times 5, 15. So since 15 is not 0, AB is invertible. So in summary, we have the following. Okay, I think I have to take it step by step. Determinant of a product tells us that determinant of AB is determinant of A times determinant of B. Invertibility means A is invertible if and only if the determinant of A is not 0. Okay. If it is 0, then it is not invertible. Then determinant of an inverse. So the determinant of A inverse is simply 1 over determinant of A. Okay, I think we can even I think I wanted to show that too, that the determinant of A inverse. So the determinant of this A inverse here now is simply, so the determinant of B inverse for in this case is going to be 3 times 1. You have 3 times 1. Okay, I think this is a kind of check. So just I want to check. So to check, right, you want to see that the determinant of B inverse is equal to determinant of 1 minus 2 minus 1, 3. So that will be 3 times 1 minus 2 times minus 1. That will be 3 times 1, 3. All right. Minus, this will be minus and minus plus 2. But this is 1. Of course, this 1 is simply 1 over 1. All right. But it's because it's 1, it's difficult to verify that. I think I could do it in this case, right? Okay, we didn't find inverse here, so I think that will be not necessary. But I mean, that's how it works. For singular matrix, if the determinant of A is 0, then A has no inverse. Okay? Then we have product and invertibility. If A is invertible and B is invertible, AB is invertible, their product. Then singular and any. So if you have any matrix A which is singular, no matter what B is, the product of A and B is going to be singular too, because as far as one of them has a determinant of 0, it's going to affect the product. So imagine this now. Let A be 2, 1, 3, 4, and B is 1, 0, 2, 1. Find the determinant of AB. Of course, the determinant of A is 8 minus 3, which is 5. And this is 1 minus 0, which is 1. So the determinant of AB is 5 times 1, 5. If the determinant of A is 5 and the determinant of B is minus, find the determinant of AB, that's simply minus 10. Find the value of K for which the matrix A is not invertible. So for this to be not invertible, it means that you have K squared minus 8 equals 0. Okay? So K squared minus 8 equals 0. To find the value of K for which this matrix is not invertible, so K2 4K, right? A is K2 4K. K2 4K. If, let me call this K, let me call it something else. L is K2 4K. If L is not invertible, okay, what that simply means is that the determinant of L is equal to 0, right? So what's the determinant of L here? That would be K times K. That would be K into K minus 4 into 2 is equal to 0. So that means we have K squared minus 8 equals 0. Okay? So that means we have K squared equals 8. That means K is plus or minus square root of 8. So that is K is equal to plus or minus 2 root 2. So if K is 2 root 2, then it means that that matrix will be not invertible. Okay? Especially this, I don't know if the sign has is really of importance there, so we can check that. So 4 to 6 now, or maybe 4 to 8, 4 to 7. Tell me whether the matrix is invertible. Of course, this is not invertible because 6 minus 6 is 0. If determinant A is 4, find determinant 2A. Determinant 2A will just be 2 times 4. That's 8 because to just multiply. Suppose determinant A is 3. Find determinant A inverse. It's just 1 over 3, all right? Because determinant of A inverse is 1 over determinant of A. A is this and B is that. Verify the determinant A, B is determinant A times B. So multiply the two, find the determinant, and find each individual one, which I did before. Okay. So we have now if AB is invertible, what can you say about A and B? If AB is invertible, A and B are also invertible. Justify your answer using determinants, of course. If AB is invertible, that means the determinant of AB is equal to is actually a determinant, right? Then and if the determinant of AB is a given determinant, let's say K, so the determinant of AB is actually determinant of A times the determinant of B, like that. So find the value of X for which the matrix is invertible. Okay, so that means X squared minus 2 is not equal to 0. Okay, So maybe you can find the value for x for which it is invertible first. It is not invertible. So x squared minus 2 is 0. That means x is equal to plus or minus 2. So if x is equal to plus or minus 2, then it means it has no inverse. So then it means for x not equal to plus or minus 2, this one already, it's already always invertible. Show that if determinant of a is 0, then determinant of a squared is 0. Of course, determinant of a squared is determinant of a times determinant of a, which is 0 times 0, 0. So with this, I come to the end of this interesting video about properties of determinants. So it can help you work faster if you understand most of these rules. Okay, let me know how helpful this is for you, and if there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can actually become a member of the channel by clicking on join. All right, that gives you some special privileges, you know, like you get to see some videos first, or some videos are only made for you as a member of the channel. And of course, you can we can also hang out and do all of these things to talk about anything that interests you on my channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.